Hello and welcome to Podcast.init, the podcast about Python and the people who make it great. You can subscribe to our show on iTunes, Stitcher, TuneIn Radio, or add our RSS feed to your podcatcher of choice. You can also follow us on Twitter or Google+, and please give us feedback. You can leave us a review on iTunes to help other people find the show, send us a tweet or an email, leave us a message on Google+, or our show notes, and you can also join our community. Visit our new discourse.pythonpodcast.com forum for your opportunity to find out about upcoming guests, suggest questions, propose show ideas, and just get to know the hosts. I would like to thank everyone who has donated to the show. Your contributions help us make the show sustainable. For details on how to support the show, you can visit our site at pythonpodcast.com. Linode is sponsoring us this week. Check them out at linode.com/podcastinit and get a $20 credit to try out their fast and reliable Linux virtual servers for your next project. I would also like to thank Hired, a job marketplace for developers and designers, for sponsoring this episode of Podcast.init. Use the link hired.com/podcastinit to double your signing bonus. Your host tonight is Tobias Macey, and I'm interviewing Craig Citro and Robert Bradshaw about their work on the Cython project. So, could you guys introduce yourselves? Why don't you start, Craig?
Hi, I'm Craig Citro. I'm a software engineer in the Seattle area.
What about you, Robert?
So yeah, I'm a software engineer in the Seattle area as well, working for Google.
Yeah, I should have said I work at Google with Robert.
And how did you guys get introduced to Python?
So I originally got introduced to Python when I got involved with a project called Sage, which is an open source math software system, which uses Python for a lot of the moving parts and for sort of gluing all of the various libraries that are included together. And in particular, Cython, a large chunk of the motivation for Cython came out of work on Sage. There was, one or two other projects that kind of had a big influence there as well, but Sage was definitely one of them.
This can feel like deja vu. I was William Stein's advisor. He started Sage, so kind of the both of us, used to be grad students in math, and so I was, working on Sage as a side project when I should have been doing my thesis, and then I started hacking on Cython as a side project when I was intending to work on Sage, and through all of it, I learned Python as well, so that's where I come from.
Yeah, I should say I met Python the same week I met Robert, because there was a workshop I went to, and Robert was randomly assigned as my roommate. So that one worked out pretty well for both of us, I think.
It's an interesting story and pretty humorous how you've managed to escape a side project with a side project. So, can you guys explain what Cython is and how the project got started?
It started out as Greg Ewing actually had a project called Pyrex back in the day. And the idea was that writing C extensions by hand is very tedious. Doing things like, getting the reference count right and working with Python C API directly. And that's the kind of thing that computers are good at. So he created this project called Pyrex, which was a Python-like language that then compiled down to C. And that's what Sage was originally using. And then we started hacking on it and extending it in ways that he did, kind of taking it in further directions that he wasn't taking his project. So Cython is actually a fork of the Pyrex project. And we knew we kind of had our own project when we had, I think, kind of what kicked it off is there was like this group of firemen who were downloading all of Sage, which is like this gigabyte tarball, just to use what was called at the time SageX, which was our fork of Pyrex. And kind of at that point, we said, well, maybe we better spin this off into his own thing. And so we grouped up with Stefan Bonnell, who is maintaining another fork of Pyrex, and created Cython.
And, to offer some more background, what we used it for there was basically in Sage, there's a lot of stuff you do. I mean, there's a lot of stuff you do in Python where it just makes sense. You kind of have these high-level objects. You want to, introspect on them and do sort of very naturally fitting things in Python, draw pictures, things like that. But very often, some of the computations you need to do are these, traditional sort of like tight sequences of for loops where, there's a lot of computation done, something like matrix multiply is a good example here where, you can think of it as I'm going to do several loops over this and paying an extra little bit of overhead for every single one of those operations just made the whole thing sort of pointless. So Cython, originally Pyrex, and then Cython was the hook where we could, take just the pieces of the code where performance was really an issue and just basically move those down to C without it being a lot of work to rewrite everything on top of the Python C API. And, Pyrex and later, Cython grew to sort of fill exactly that role. It was the way to take just what you needed and make it fast without having to rewrite everything as you went.
And can you guys explain a little bit of the syntax of Cython and how that interoperates with the Python language itself?
Yeah, so it's nearly a superset of the entire Python syntax. So basically, you take Python and then you annotate certain variables or functions with type information. Is kind of the key extension of the Cython language. And then if you have type information, like for instance, if you just declare something to be a C double or a pointer or something, then you can do all the C operations on it without the Python overhead. There's also another use case which hasn't been alluded to, which is when you're trying to wrap a C library. We have a syntax for declaring the functions that are available in the C library, so you can call them directly. So it's good for writing wrappers as well as making your Python code fast. And for both of these, we try to extend the Python syntax in kind of a Pythonic way. So it's just kind of like minimal extensions. And then pretty much if you can read Python, you can read Cython.
And does the new type hinting in Python 3.5, are there any plans to take advantage of that as a way of annotating the Python code or modifying the annotations you guys support, or would that just be too much work to modify the syntax that's already been created?
There is a lot of thought to maybe doing that. One of the things that's interesting is that the type annotations are not contracts. They're more like comments, at least in the Python 3. So versus, when you give a type in Cython, it's really a contract that if this thing isn't a double, like we're going to make it a double. And the other thing that is difficult is it doesn't have any way of kind of declaring external types and declarations. If I want an array of pointers, that's not very expressible. And then the third thing that's hard is a lot of the speed can be gained by making sure that your local variables are typed. And there's no way to do that. The Python function annotations are really about your function interfaces, and you can lots of times from the function signatures infer a lot of information about the internal types, but not always completely. And really, if the integer that you're looping over is typed is kind of a key thing where Cython can gain a lot of speed.
Right. And a couple things that you mentioned in there. So you were saying, for instance, if you annotated a particular variable as being a double, it sounds like you're saying that you will actually explicitly cast that to being a double. Is that correct?
Correct. So if I assign a Python variable to that, if I have a Python object and I assign it to something typed as a C double, I'll actually, force it to be a floating point number and extract the C double out of it. And then in the generated code, it will be a C double from then on.
If it turns out that it's actually an incompatible type, then when you actually run the compilation, it'll generate a compiler warning or a compiler error?
So if we know it is, it'll be a compiler error. But of course, since Python is dynamically typed, we may just say, oh, X is an object. I'm going to treat it as a double now. And the best we can do is throw a type error at runtime because X happened to be a string rather than a float or an int or something.
Okay, so if you do have incompatible types, then there's no guarantee that the compiler is going to check it because of the dynamic nature of Python, and you might still end up with runtime errors unexpectedly. Okay.
Yeah, kind of the default type is the object type. Objects is coercible to anything except at runtime.
And my understanding, too, is that Cython can improve the performance of a Python program without having to provide any type annotations. Curious how it manages to do that.
Yeah. So one of the things is that it cuts out on the interpreter overhead. So instead of having a bytecode and then a little virtual machine, it actually basically produces the C code to call the C API calls directly, and that usually buys you anywhere from a factor of 1.5 to 4, depending on your actual program. So then the other thing we can do is we can infer a lot of the types. So if you have x equals 1.5, we actually infer that to be a double. And then a C double, and then manipulate it as C types. Or if you have, for, I in range 1 to 10, we say, aha, I is going to be a C integer, rather than actually creating this, range object by calling the Python to get a list of Python integers and so on. So there's a lot of type inference that we can do that can speed up your code as well.
All the type inference, unless this has changed recently and I didn't know about it, all the type inference that happens sort of within the body of a function. This is also, sort of complementary to the kind of thing that you would want to do with type hinting.
you were mentioning, for instance, if the variable has a value of 1.5, you were saying that it would be cast as a C double. I'm wondering if you prefer doubles in general because of their greater precision, or if you will just, or if you do use floats liberally as well.
Well, we use doubles because that's what Python uses for its floating point. So there's kind of a Python float is under the hood a C double. So, yeah. You could explicitly declare it as a C float, but if you really wanted to.
Okay. Yeah, because I know that Python also has the concept of a double that you can explicitly set something as, so I wasn't sure. I didn't realize that under the covers, floats are run as doubles as well at the C level, so that's interesting.
Yeah. Also, ints are longs under the hood.
Yes, that part I did know. And I know that one of the things that they changed in the 3x series was how those longs get upgraded at certain boundaries. I don't remember the details of it, but...
Yeah. No, integers are actually one of the really tricky things because you want to be able to infer them because C ints can be, a factor of 500 faster than Python ints. On the other hand, you don't want to overflow things. So pretty much if you just take pure Python code and compile it with Cython, the criteria is that it should behave exactly like as if you ran it in Python, except for hopefully faster. And so, for instance, if you assign something and we only infer things by default to be integers if we can verify that they won't overflow. So, for instance, if you have x equals y plus y, and we thought y might be an integer, but we might not be able to tell that y is a small enough integer that y plus y won't overflow if we make it a C int. And so in that case, we have to say, well, x has to be a Python object because it might be too big. So integers are really, really tricky because I would say 99% of the time, you're not going to overflow, but it's that 1% of the time it's going to bite you. So we can't infer that and then, have, a silent wraparound overflow where Python will give you just a bigger value.
Handling numbers in computation is definitely one of the trickier things around because of those overflows and the byte ranges, or the byte boundaries.
I mean, even just basic things, right? Like if I do a for loop over something that's larger than a C int could ever go to, the whole non-terminating thing will definitely be a bad behavior change for your program.
So can a Cython module be used as a way to sidestep the GIL, and what are some of the pitfalls that can be caused by doing so?
So what we have is we have a way of declaring functions or portions of functions as not requiring the GIL, in which case the GIL will be released during the execution of those functions. And so there's a limited number of things you can do. For instance, you can't actually, the GIL is very pervasive, so you can't even do reference counting without the GIL, so you can't manipulate Python lists and dictionaries. But if all your types are C code, or for instance, you're reaching into a list but you're not modifying it, you don't actually need to do any ref counting, you can release the GIL and then do a whole bunch of stuff. And in the meantime, Python threads are actually real threads that just have this global lock. Other threads can be going along while you're turning away in the C code without the GIL, and then you reacquire the GIL when you exit this block or exit this function. This is also useful sometimes when you're calling external libraries, and they obviously don't need the GIL. So if it's going to be a long call, you can declare them as you release the GIL, call the library, and then when the call returns, then you reacquire the GIL.
And it's worth noting sort of I'd mentioned that a lot of people, the way they use this is, you start with some pure Python code and, you take bits and pieces where you've already discovered you have performance constraints and you move those, you sort of annotate those in Cython so that those get moved down to sort of pure C. Well, if you find that you have a block of code that the whole piece or the whole function, right, which is sort of a natural boundary for Python code, the whole function happens to be basically executing in C, then, lo and behold, suddenly you don't actually need the GIL before, until the end when you're looking to return. So you can annotate that. And, it's just one more nice lever for ways that you can, once you've sprinkled in a little bit of annotation and found out what's going on, it gives you a hook to, get yet more performance out of it, depending on the model of, what you're doing.
And we don't let you do unsafe things with the GIL. So one of the pitfalls in trying to code C extensions by hand is knowing when you have and when you don't have the GIL and what you can do. And so, for instance, if you've released the GIL, it's a compiler to do anything that requires the GIL.
We've talked about it a little bit already, but can you give some other examples of how Cython can be used to improve the performance of Python programs? And I'm also curious about what the natural boundaries or natural sizing is for Cython subcomponents of a program, or if it's common to use Cython for compiling an entire module or application even.
So I can take the first part of that, and then Robert can give you sort of the more exotic answers because he has more familiarity with the bigger examples. But the first thing that people do is sort of what I was mentioning before. You have your application. It does exactly what you want. You've basically written it in Python, and you've enjoyed all of the things that people enjoy about Python, right? Like it's quick to write, it's quick to get up and running, you can experiment easily. And now what you found is that you have some sort of performance constraint. So Cython actually gives you a few interesting tools for profiling and things like that. I mean, you can sort of run your code through Cython and get some C code out and try to profile that directly with existing C profiling tools, which is often quite helpful and sometimes maybe not what you want. One of the things that Cython has is this annotation mode where you can spit out, when you ask Cython to compile a file, it'll actually spit out alongside it an HTML file, which is your source code. And the various lines will be colored from white to, is it still dark yellow? Last I looked, it was dark yellow. Okay. To dark yellow. And the darker the line of code, the more Python C API functions that are sort of encoded in what's going on there. So now, this is not directly telling you how much time is being spent in that code, but it's a good proxy for it, that the two are strongly correlated. So what you can do is, and you can actually also, just to sort of learn how Cython works, you can also take one of these and just, click on it, and it will expand to show you the code that this original line of Python or Cython became. So you can use this to sort of identify places where there are hotspots in your code in terms of how much time is being spent pushing data back and forth from Python into C, or paying the price of using a Python object. And then if you look at that and you say, well, gosh, there's a whole bunch of, activity going on here, and I know that this is just, a loop control variable that's never going to go above 100. I'm not going to do anything exotic with it. It's really just a counter for me. It's the perfect spot to say, oh, okay, well, I'll just tell Cython, hey, you know what? Go ahead and make this a C int. I'm okay with that. Or make this a C string. I'm okay with that. And you sprinkle a few annotations in, then you repeat the process, and you can, reprofile or, spit back out another annotated file and look at what happens, or, just run your whole app again and see, where your new hotspots are. And maybe they're all gone. The examples, if you find any talk on Cython, the first example that people always offer is, you have some trivial, triply nested for loop where it is exactly the kind of thing where everything can just be pushed into C, and you can sprinkle, 2 or 3 lines in, and then magically the function, of course, for obvious reasons here, runs just as fast as it would have if you'd written it directly in C, but it looks a lot like Python and plays nicely with the rest of your Python code.
Yeah, I mean, I think that classifies how optimization works in general. One of the nice things is, so with a lot of, before Cython Pyrex, what you would do is you would write your thing in Python, and then if some part was too slow, you would have to rewrite that in C, possibly introducing new bugs and debugging and everything. And then you'd have to write some wrapper to go back and forth. And also this boundary was very ossified. It's kind of like, in Python, you're above the land, and then you drop down in C, and you're like completely under the water in a completely new language with, different conventions and, a lot of hoops to jump back and forth. And the nice thing about Cython is it really lets you just take this little tiny bit of code and say, this is the part that's too slow. Today, I'm just going to optimize this. And then you can run along, and then, maybe 2 days later, you're like, oh, and actually this part here, I'm going to do that too. And kind of like every little type you add gets you one step closer. And you have this really gradual slope where you can kind of sit anywhere on the, how much do I care about performance versus actually trying to profile and annotate my code versus, a lot of, it's kind of the, 90% of your time is spent in 10% of your code, and allows you to spend time on that 10%. You don't even have to identify that 10% ahead of time, because as humans, we're notoriously bad at detecting where we're actually going to be spending our time, especially as a program evolves. And just, on an as-needed basis, you profile and you say, oh, this is the little spot that needs to be a little bit faster. And then you add some hints, and sometimes that drops to 0. And of course, when that drops to 0, you see another hotspot somewhere else. You can go and optimize that. So in terms of compiling the whole program, kind of the second part of your question, usually you don't compile your whole program. You profile to figure out what parts of your program actually matter to compile, because there is this extra step involved where you have to invoke the Cython compiler to produce a C file, invoke a C compiler to produce a shared object library, and then load that into your running session. And that is higher overhead than just Python itself. But just like Python, Cython is organized into modules. So instead of py files, you just have pyx files. And you can C import as well as import from pyx files to pyx files so that they share C types as well as Python types. So you kind of organize your code exactly the same way. And then you say, well, this module is going to be a compiled module because I'm, hinting some stuff in here to be fast. And then, usually I'd say the bulk of your code is just Python because the bulk of your code is not performance critical.
And so once you've compiled down that shared object file, do the regular Python imports that you already had in your code still work, or do you need to change the import mechanism that's used for loading that object?
Nope, they all just work. So it's the same as any other Python C extension where when you say import foo, it looks for a foo.so file in the right place, or foo.dll or whatever your system happens to have, and loads that. I can turn a module into Cython, and people will import it and not even notice that it's been changed.
And could Cython be used as a way to help developers understand how their code performs under the regular CPython interpreter?
Yeah, yes and no. You definitely can use it to get some information. I was sort of mentioning this before. If you look at the annotated output from running Cython on a py file, it'll show you sort of how much that one line of code corresponds to activity that's happening under the hood in terms of the Python C API. But of course, that is not the only aspect of performance, right? You still need traditional profiling tools, some of which play very nicely with Cython, and some of which, you have to sometimes do a little legwork to get going.
Yeah, you can definitely see how much interaction there is with the CPython API. But, some CPython calls are 100 times faster than others. So from a raw performance perspective, it's usually what happens is you profile your code and you say, I wonder why that is slow. And then you go look at it, and then you identify a culprit. But the problem is if you just try to identify it ahead of time, lots of times what people will do is they'll look at it and be like, oh, God, this is touching objects all over the place in ref counting. And they don't realize that, despite the fact that it's doing a bunch of ref counting, it runs in 5 nanoseconds. Whereas this other piece of code that only, makes one call out to the C API is actually doing something really expensive. So. And
we've already talked about it a bit, how Cython works under the covers. I don't know if there's anything else worth digging into there.
Kind of the, high level thing is it turns your Python file into a C file and then compiles it as a C extension.
It might be worth noting that, by and large, Cython also isn't, sort of inventing its own practices for how your compiled code is going to play with Python, right? It's just using the Python C API. A not unreasonable way to think about Cython, which Robert mentioned earlier, is, it's a way to make it so that you can avoid ever having to learn the ins and outs of the Python C API yourself, which, if you've ever used the Python C API for anything fairly serious, you will appreciate greatly.
Fortunately, I have not had to dig down to that level, but if I ever do, I'm sure I'll be reaching for Cython pretty rapidly. So what were some of the challenges that you guys encountered during the creation and maintenance and evolution of Cython, and what are some of the design decisions that you made to overcome those challenges? One
design decision that's still with us, unless been quite a bit of activity that I haven't noticed lately, is the parser is largely a large chunk of code, and the language that it parses is whatever the parser happens to accept. Robert should correct me if this is no longer the case, but that for anybody who's ever written a compiler, right? Like you have this principled view of the world where you're going to just write down your grammar and everything will be generated from there, and you can just sort of model things on top of that, but then you end up with a few corner cases, and trying to make those changes later can be tough and troublesome.
Yeah, definitely. I would say so we do have prototype grammar for Cython, but it's not used yet. And certainly mixing the parsing of C types with the parsing of Python is an interesting experiment. And another challenge I'd say is anytime you want to add extensions to the language with care, because anytime you add anything, it's going to be there forever, pretty much. And it's really easy. Like a lot of it is look good on surface, but you end up with this mess if you accept everything. And so you really want to, try to stay close to Python and say, is there a way we could express this, very cleanly using the syntax we already have, rather than trying to, invent our own thing and diverge from Python itself? Because the further you go from Python, the harder it's going to be for anyone who is reading this code to understand what's going on. And so I think that's one of the things we've tried to do is stay close to Python so that anyone who knows Python can just, read a Cython file. And you almost forget that you're reading Cython sometimes until you're like, oh, look, there's a type annotation. That's not legal in Python. Oh, yeah, I'm not in Python.
Yeah, Robert also, hit on this one before, right? But like the compatibility with Python, not just in terms of syntax, but also in terms of semantics, is a really interesting design constraint, right? So, for when I was finishing grad school and Robert was finishing grad school around the same time, Robert and I used to talk to him driving home, 2 or 3 days a week, because I would like drop him off on my way home just to get a chance to chat longer. And I could characterize most of those conversations as basically we would start a conversation about a cool new idea that one of us had for, an optimization that we could make. And over the course of the, 15 or 20 minutes we were driving and the 5 or 10 minutes we'd be chatting after that, it would turn out that basically it sounded really good on paper and we could easily make it work, except that there are these like 2 corner cases where we'd actually be breaking the semantics of Python itself if we tried to do this. And then we would, try to figure out if there was some sort of static analysis that we could do that would make it so that we could still pull off this optimization in some cases. And almost universally, the answer would be no, unfortunately, we can't do that without breaking, compatibility with Python itself. So this has been a very serious design constraint. And the way we've overcome it is just, if there are certain things that if you want them, you simply have to provide an annotation or, give us some other information yourself in order to let us be able to take advantage of, some potential optimization.
And have you guys ever submitted any PEPs for introducing any new syntax or utilities into the Python language and Python interpreter itself to either simplify or improve some of the work you guys are doing in Cython?
I haven't. The one PEP that I've toyed with, which I think the feature's almost there already, is a lot of the code is plagued with dictionary lookups. Like if you look at Python, really it's just like there's this big pile of dictionary lookups. That's what you're doing. You're looking up things in dictionaries.
Yes.
And when you do a method call, for instance, in a loop, it would be really nice if there was some cheap way to say, you know what? I did this dictionary lookup before. I want to be able to know if the result has changed. And so, if dictionaries had like some kind of a dirty bit or number that could be intermitted. And I think there's something like that with method caching on types. And I don't know if dictionaries have this per se, but that would be really handy. If I was going to submit a PEP, it would be that. So you don't actually have to see, is c.foo the same foo that it was, 20 milliseconds ago? And so.
Didn't DAG do some PEP related to, or was it just something that got into NumPy? I thought he did a PEP for something related to something with the way he was doing layout and strides and
Yes, so Cython, I guess the Cython implementation of buffers influenced the new buffer PEP API.
And when you say DAG, are you talking about Dag Bradley, the RX Python maintainer?
No, Dag. I don't actually know how to say his name, which is why I only said Dag. But it's Dag Sver Seljabotin. I think
that's right.
If he's listening, he can laugh at me at how poorly I pronounce his name.
All right. So does the cross-platform nature of Python create any unique challenges when you're working on generating and compiling the C code?
So yes and no. We have the advantage of auto-generating code. So if you look at Python, like the first 1,000 lines of your Python code are like a whole bunch of macro system, specific defines and everything like that. And so we're able to, when you compile your C file, it actually works on a variety of platforms and the same C file. So if you compile it on Windows, say, then the same C file will compile on Linux or OS X. For Python, I believe the earliest support now is 2.5 up through 3.5. So we really abstract away all these details, and it's getting them right the first time is kind of tricky. But once we're able to basically, make macros for all the things we have, it doesn't matter how ugly the generated code is. When you actually compile it on the system, these macros all expand to exactly the right thing. So it's actually better than writing C API by hand because you don't have to be like, well, every time I'm making this call, I have to remember to do this thing if I'm in Windows and that thing if I'm not. You can just abstract that away.
I mean, there is one small difficulty, which is just that if you, at install time for a package, if you write a package that just uses Cython, depending on how you've done things, right? I think most people basically just can either include compiled.sos, or, in a wheel or whatnot for some of the common operating systems. But if you do need somebody for various reasons to be able to basically start from your original PYX file, then run Cython, and then run the C compiler, I mean, it is just a higher bar, just as it is with any Python code that happens to include C extensions. But, it's one that is easier to incur than, taking the time yourself to write your own C extension from scratch. So, it's one that we hit maybe more often than the average package.
In some sense, we make it so easy to write C extensions that then you by yourself when you find people, trying to run your code on systems that don't come with C compilers. So,
as an extension to that question, what processor and system architectures does Cython support, and are there any plans to expand that support to new systems or new CPU architectures?
We pretty much support everything that Python supports, so C Python, I should say. I don't think we do any platform-dependent things. We're pretty strict at trying to stay at C89 and staying within the standard of well-defined behavior. So, for instance, we don't rely on generated assembly or special hacks about how integers work in some cases. I mean, we even have cases where, for instance, overflow signed integers is undefined. So what we'll do is we'll cast everything to unsigned integers, do the arithmetic there where it's defined by the C standard, and then cast back into signed integers to avoid any architecture-dependent behavior. So, of course, if you write code that depends on architecture-specific behavior, for instance, char being signed or unsigned, that, if you're using a char, it'll be signed on the systems that is signed and unsigned on the system that is signed. And, that kind of leaks through. If you're using C types that have undefined behavior, then we can't really do anything there.
So how do generators and list comprehensions look in C, and did those higher level language constructs pose any special challenges in the design and implementation of Cython?
I mean, if anything, they were sort of a situation where there was the chance to do something a bit better, but Robert should really say this because he wrote all that code.
I would say Cython has a lot of go-to when you look at the generated code, and that's because we're trying to emulate the control flow of one language using another language. And so as well as C types, you can also declare objects that are kind of CDEF objects that have an underlying struct and have members that are C objects. And we use the same thing for like generators and lists, and where we actually create a struct representing the state of the interpreter. Then, I mean, basically, a lot of the higher level features like generators are really just a cheap way of creating an object that has an iter method that remembers what its state is at every point of execution. And so we emulate that in C by creating an object that when you call like the next method, all the stack variables are actually contained in the struct of the object itself. And I don't know there's much more to say. I mean, it's basically we look at what the spec is, we emulate it in C, and we try to pull stuff off the C stack to emulate the fact that Python's stack is much more of a flexible object than C's stack.
Part of the reason that we wanted to have you guys on is I've actually been following the Cython project for a little while, but it's also come up a number of times in other episodes that we've done. For instance, when we were speaking with the folks at Kivy, they make pretty heavy use of Cython for being able to target the Android NDK. I know that Pandas uses Cython to optimize some of their operations, and it's pretty popular in a number of data science libraries. I don't know if you guys have any sense of which sorts of industries or problem domains tend to make the heaviest use of Cython, or any insights into how it gained such great popularity and widespread use?
I mean, definitely for sort of scientific applications, right? Where, if you think of the kind of the place where Cython can give you the biggest advantage is where you kind of want to be writing C code, or rather the code that you're writing could be written just as well in C as it is in Python. And what you want to do is sort of quickly pass from I happen to be in Python with some objects and libraries that I care about down to I'm just going to write a bunch of for loops that are nested inside each other. This is very common in scientific applications, right? Like we often joke about these sort of, nested for loops that you find everywhere, right? If that's what your code looks like, Cython is an incredibly powerful tool because with just the tiniest bit of work, you get all the advantages of having written it in C with none of the downsides of, manual memory management or anything like this. And it plays very nicely with existing Python code. So partly just in terms of timing and people that we were interacting with. So Sage, Sage has been, the Sage developers and the IPython developers have had close communication for years. So, we were talking to the IPython and SciPy and NumPy folks since, 2006, 2007. So, I mean, it sort of worked its way in there very early. So for a lot of the scientific applications, it's a natural fit, and it's just been around long enough that it's just been picked up very well. As far as other areas where, there are obvious use cases for it, I mean, like what Robert was mentioning, if you have an existing C library that you want to wrap and expose into Python, Cython gives you sort of one good way to do this with a lot of sanity. The other common way of doing this is to use something like Swig, which, as anybody who's used it will attest, often involves quite a bit of insanity. The contrast there is that Swig will automatically generate you a wrapper for a library, and Cython cannot necessarily do that depending on how things are laid out. So it's you sort of have a choice, but places where you're wrapping existing C code are just a natural fit. So, any sort of shop where they have some existing stuff, especially like networking libraries or things like that. I mean, for instance, one of the Google projects, gRPC, which has a networking library written in C, they expose that via Cython. So, it's a really natural fit in situations like that. Robert probably has some other good examples.
Yeah, I mean, I just want to comment on the wrapping stuff. Cython does force you to actually manually write a wrapper, but this is actually an advantage lots of times because the way that you use a library in C or C++ is often very different than you use it. Because lots of times the C or C++ library is worried about things like memory management, lifetime of objects, and if you just expose those APIs to Python, you really usually don't get a very Pythonic API. And sometimes you'll even get an API that can segfault if you're like, oh, I have to manually allocate this thing before I can, call these methods on it. And so Cython gives you an opportunity to not only expose the C library, but you can create a more Pythonic interface to the library, which is without incurring a whole bunch of overhead. And then I think this is one of the areas where Cython is used a lot. I think also the numeric community, scientific community, uses Cython a lot because people play the role of, on the one end, they're doing experimentation and prototyping and, trying to play with a bunch of ideas. And then 4 hours later, they're I want to run this on my supercomputer. And, I only have 4 hours. And if I can make my code run 10 times as fast, I can, do it on 10 times as big of a data set. And so it really fits this niche nicely of, you want a very high level language to play with. And then you want to be able to optimize things because at the end of the day, I just want to add a billion doubles together in the right order. And this is very different than say a lot of professional programmers who, when they sit down to write a project, they say, well, I'm just going to choose a language that's insanely fast because this is what I do for a living, and I already know I want it to be fast. And kind of skip the prototyping experimentation stage a lot that scientists have. It's also used a lot outside. For instance, the other primary developer is the leader of the LXML Python project, and that's obviously not scientific computing. It's a lot of string processing, and there's a lot of benefits for having low overhead for parsing XML documents. That there's a lot of kind of low level manipulation that kills you death by 1,000 cuts if you do it in pure Python with object allocation and string manipulation. So I think pretty much anywhere there's a need to take some Python code and interface with an existing C library or just make it faster. There's interest, and the scientific community has its fair share of those problems. So that's why it's been accepted a lot there.
Extending that a little bit further, I'm just wondering what some of the most interesting and crazy uses of Cython are that you guys have seen out in the wild.
What was I forget the story, Robert, but you pointed this, you mentioned this one earlier. What was the story with the firemen?
We don't know what they're doing, but they're downloading a gigabyte of Sage to get our, 5 megabyte package and pull it out and use it. So I actually never hunted down what they were using it for, but I can't think of anything way out there that comes to mind. I mean, I remember being surprised, but I can't remember any of the specific instances. I mean, I know there's a lot of fairly serious number theory stuff that's done in Cython with my experience in Sage, where you have these it's an interesting blend of, you have these very high level Python objects like elliptic curves, and you're able to boil this down to a problem that involves manipulating millions and millions of integers in the right way, looking for a certain combination of the things that add up. And it really is this enormous span of levels of abstraction, because at the one end people are very concerned with getting things to fit within a 64-bit bit integer, and on the other hand, they're dealing with these things that like you still don't understand after you have a PhD. So
this question, I'm sure, is a little bit out there and probably unrealistic, but would there ever be potential for Rust to be a compile target for performance and safety optimized modules?
It depends on how similar Rust is to C. I remember looking into Rust at a high level, but I haven't ever coded in it.
Yeah, from a syntax perspective, it's pretty divergent in my understanding, and I know it's possible to write Rust modules that can be imported in Python because it does have the ability to be compatible with certain C modules, and I think you can call into the Python C headers. But from a syntax perspective, it's pretty wildly divergent, and it has a totally different memory model. But just curious because of it being the sort of the new contender at the systems level for a performance optimized systems language, as well as its memory safety guarantees.
Something you could do, this is not compiling down to Rust, but something you could do in the same ballpark that might be, the kind of thing that somebody would need to use this for. You could imagine basically saying, look, I have a chunk of Python code, or I have, maybe a large swath of Python code, and I have some Rust code that I really want to interface with it. Maybe it's Rust in Python, maybe it's Python in some other language, right? But while not every language has an easy way to interoperate with Python, just about every language under the sun does have an easy way to interoperate with C. So you can use Cython as sort of your shim to say, well, Cython is kind of a clean way for me to, declare and move a chunk of this down, or basically, manually expose a little interface that can take my chunk of Python code and go down to C. And you can imagine, in that other language, whatever it's going to be, doing the same thing on that side, and then sort of using that as a shim to push the bytes back and forth at the bottom. So using this as a hook for calling between, Python and some other language that you have to interface with. I mean, you would still have to do a little bit of legwork. This is the kind of thing where the first person who does it will have a really hard time. The second person who does it will have a pretty hard time. And then after that, it'd be pretty easy. But it's, it's the kind of thing that we have tossed around as an idea once or twice. Like, oh, maybe I could do this by, wrapping this thing and using Cython and then going over here, and it didn't ever, materialize, but it's something that's definitely doable.
Yeah, certainly. If you have a Rust library that exposes a C API, there have been a lot of times when what people are wrapping is not C code. They're wrapping, C++ code. They're wrapping Lisp code. They're wrapping D code. That happens to expose a C API, and then we can call that. So C is kind of the lingua franca of form and function interfaces. I would say that actually it might be difficult because a lot of the stuff we do in Cython, when we generate the output of the code, looks unsafe. So we have all sorts of pointers that we're casting to all sorts of random types all over the place. And we can do this in Cython because we know, for instance, that this thing that's a PyObject star is actually some special struct because, it was constructed in such a way. And, we checked for it earlier by checking some bit on a field is, the types match. And I think it would be really hard for a language like Rust to understand these checks. For instance, to understand that we never take this branch that does this unsafe-looking cast unless we know this cast is actually safe. So that might make it difficult to compile down something like Rust because it would say, oh, you're not allowed to do that. And in fact, we've kind of already put the guards, and the guards are scattered all over the place and not in a very declarative form. So that might be an interesting challenge if you wanted to have other backends that weren't as liberal as C. But on the other hand, since we start with Python, the opportunity to get things wrong, unless you're manually calling malloc and such, is much lower. So the benefit to compiling to Rust, kind of, I guess, I'd say Cython is, I won't say it's as good as Rust, but it is, leveraging CPython and CPython's garbage collection and stuff. Kind of the sanity check to say what you're doing doesn't make sense. Then the code that it generates is going to be this crazy code that does all sorts of unsafe casts and, pointer dereferencing that it knows due to the higher level of the code that is now lost are safe.
So are there any questions that I didn't ask that you think I should have, or anything else that you'd like to bring up before we move on?
That I can think of, no.
Okay.
Nothing comes to mind.
Great. So for anybody who wants to keep in touch with you guys and follow what you're up to, what would be the best way for them to do that? Why don't we start with you, Craig?
You can find me in sort of the expected places. I'm on Twitter. I have a GitHub account. I have a web page. If you just Google my name, you're almost sure to get me. I'm one of few Craig Citros out there. and I'm easy to track down.
How about you, Robert?
Yeah, my name is definitely much more common, but if you Google me and put something in there like Cython, then you'll find my email. I don't really have Twitter or anything. Email is definitely the best way to get a hold of me. I'm not that good at keeping up with it, but I'm definitely better at keeping up with that than any other form of communication. So that's probably your best bet.
I found that if I want to get a hold of Robert, the easiest thing to do is to find him in person. So if you want to just go ahead and get a job at Google, that's an easy way to find him.
So I guess with that, we'll move on to the picks. I'll get us started tonight. So I'm going to keep it short. My pick tonight is actually a pretty interesting blog post from some of the folks at MIT. It's a post called Certificates, Reputation, and the Blockchain. And it's about how they were doing some research and experimentation into leveraging some of the blockchain technologies as a way to more easily and permanently track people's reputation and certificates and achievements in a way that is provable and more difficult to forge. And they do a really good job of likening it to the notebooks that journeyman carpenters in Germany used to carry around in order to get the stamps from the different masters that they worked with, so that they could then show that to their future customers to show what their qualifications and certifications were. So interesting read. I definitely recommend checking it out. And with that, I will pass it on to you, Craig.
All right. So I thought up three as I was coming into this. So the first one will be entirely shameless. My wife has a blog and now several books. So I'll pitch one of her books, which is called The Curious Kid Science Book. So it's a first science, it's a book of ideas to explore with your kids, ages, it's sort of targeted at 4 to 8. Some of the, our 3-year-old is not quite ready for it, but, I won't lie. I had fun doing some of the experiments while she was writing it, so that's an easy one to pitch. I'm obviously a little biased given that she wrote it and my kids are in all sorts of pictures throughout it, but that one's a lot of fun. Another one is in my day job at Google. I work on tools and sort of data science-y stuff, related to Python, but also with some other languages. And we use Jupyter a lot. So the thing I would pitch is there's an R library called dplyr, which if you haven't run into and you do spend a lot of time doing data analysis, sort of dplyr and, some of the related things going on around it with like McGritter. There's probably a classier way to say that, but I kind of like the lowbrow pronunciation. It's kind of an interesting way of, just rephrasing the code you've always written, but it tends to be a lot more readable. And, having used it a bit for various things so far, I tend to find the data analysis code that I write is much less likely to be write once, read never, and much more likely to be stuff that I can reuse later. And that, for people who spend a lot of time writing data analysis code, that's a really valuable thing. So, even if you're not going to switch to using R for anything, it'd be worth checking out just to see what it might look like and maybe, pull a few ideas back with you. And I guess third, I'll pitch a book that nobody I'm related to wrote. Which is called Everything is Obvious Once You Already Know the Answer by Duncan Watts. It's, a behavioral economics book in the same vein as, Thinking Fast and Slow and some of the other ones that have been popular, like Dan Ariely's books. But he has a slightly different take, and Duncan Watts is a complexity researcher at Microsoft Research, and he's, having read his blog and, that book and part of one of his others, he just seems like a pretty interesting guy. And, I got a lot out of reading that book, and it's, I think a lot of people have heard of Thinking Fast and Slow. In fact, I think maybe somebody even listed it as one of their picks on another episode. And this is another one in the same vein, but, maybe for whatever reason people don't seem to have heard of as much. So I enjoyed it a lot.
Great. Robert, how about you?
Okay, so I'm going to start out with kids' book author. Unfortunately, it's not your wife. But I have read one of her books, and it was really fun. We did some stuff there. So Mo Willems, if you've never heard of him. Yeah, like Elephant and Piggy and a whole bunch of somewhat surrealist, but very funny for parents to read and kids to read. So that's a very fun thing if you have kids between the age of 2 and 8, or probably, or adults. So
Mo Willems, we've tried to get him voted in as the children's poet laureate for the U.S., but haven't had any success yet. Maybe we can work together on that one.
Yeah. So that'd be my first pick. Second one is just a crazy fun toy that we got the other day. Philips Hue lights. So they're basically they have red, green, blue LEDs in there, so you can make your room whatever color you want. And one of the cool things is their little hub actually has a really nice REST API. So you can totally program it to do whatever you want. And it's just listening on the REST API to do to listen to commands. So for instance, for my kids, I wired it to a keyboard so they type a color. It's educational. They're learning how to spell their colors. And then the lights go that color. So that's just been a fun toy that we've been playing with lately. And then for my third pick, I'm gonna have to go with so Sage, and most recently the Sage Math Cloud is a really fast way to get online. I did a lot of hacking on Sage, and I have to say the Sage on my computer is way out of date. But these days I'll go online when I need to do a little computation or graph something or something like that. And so you can just hop online and have a instant Sage running session. It's actually a full VM that has Jupyter notebooks and everything in there. Just kind of at the click of a button. So that's really handy if you like math, or you just want a really easy place to run a notebook.
Great. Well, I have 2 kids of my own in those age ranges, so I'm definitely going to have to check out Mo Willems, and I'll also take a pick at that Curious Kids Science book because they both like science as well.
Awesome.
Well, I definitely appreciate you guys taking the time out of your day to join me to talk about your work on Cython. I'm sure a number of other people are going to be interested to hear about it as well, and it's definitely a popular language. I've seen and heard it pop up in the community a number of times over the years, so congratulations on a job well done, and again, thank you.
Thank you. It's been a pleasure.
Have a good night, guys.
You too.
See ya. Bye.